All right, let's dive in. Today, we're going to look at a totally different side of artificial intelligence. This isn't the AI you're probably thinking of. No neural networks, no giant data sets. No, this approach is built on something much more fundamental. Pure, formal logic. It's a way to build intelligence one rule at a time. So, let's start with a really basic question.
I want you to just chew on this for a second. We are so used to hearing that AI learns by crunching just insane amounts of data to find patterns. But what if we took a completely different path? I mean, a totally different path. What if we could build an intelligence system by just telling it what's true about the world and then letting it figure out the rest on its own? And that idea, that's what brings us to our first section here. We're going to explore a way of thinking that really stands apart from mainstream machine learning. It's called logic programming, and it's actually one of the original, foundational ideas for how to make computers intelligent.
This table really just lays it all out, doesn't it? On one side, you've got machine learning. It's all about programming the how. You feed it a million pictures of cats, and it learns how to recognize a cat. But logic programming, that's about programming the what. You don't give it step-by-step instructions. You just give it facts and rules. You declare what is true, and the system uses pure logic to figure everything else out.
So, how in the world do you actually build a system on pure reason? Well, it all starts with a super solid, well-established foundation, formal logic itself. This isn't about guesswork or probability. This is all about precision.
The specific tool for this job is something called first-order logic, or FOL for short. The source material calls it the workhorse of automated reasoning, which is honestly the perfect description. You can think of it like a super precise language. It's a way to write down facts and rules about the world without any of the fuzzy, messy ambiguity of how we normally talk. Everything has a very clear, defined meaning.
And the basic Lego brick of this whole logical world is a special kind of rule called a horn clause. And it's actually beautiful in its simplicity. It's got a head, that's the conclusion, the thing that happens, and it's got a body, that's the set of conditions. The rule basically just says, the head is true if and only if all the conditions in the body are also true. It's the ultimate if-then statement, and it's the heart of this entire idea.
Okay, so theory is cool and all, but how do we make a computer actually use this logic? Well, the answer is a programming language that was designed from the ground up for exactly this. It's called Prolog, which is short for Programming in Logic.
Just look at this line of code. This is what Prolog looks like. And what's so wild is that you're not telling the computer to do anything. This isn't a command. It's a declaration. You are simply stating a fact about the universe. John loves Mary. You've just added one more little piece of truth to the computer's world.
So, how does this actually work? Well, first, it's declarative. You just declare facts, like we saw. Second, it's goal-directed. You don't run a program. You ask the system questions, or what it calls goals. For instance, you could ask, does John love Mary? And that's when the system's inference engine kicks in. It uses this core mechanism, a resolution principle, which is a fancy way of saying it works backward from your question, trying to find a logical chain of facts and rules to prove that it's true.
Okay, so we can state facts and ask questions. That's cool. But what's the killer app for all this? Well, it's building systems that can reason like a human expert in a really specific domain. We're talking about knowledge-based systems.
An expert system is, exactly what it sounds like. It's designed to mimic a human expert. And just notice the parts here. A knowledge base, which is just our collection of facts and rules, and an inference engine, which is the reasoning part of the system that deduces the answers. We're essentially capturing an expert's knowledge and their thought process in code. And this table right here, this is a perfect, tiny example of a medical expert system. We state two facts. The patient has a fever, and the patient has a cough. Simple enough. Then we add a rule. If a person, let's call them X, has a fever, N has a cough, then that person X has the flu. Now, we can ask the system our goal. Does the patient have the flu? And using those facts and that one rule, the inference engine can logically deduce the answer. Yeah.
Okay, but this all seems very rigid, right? Everything is either totally true or totally false. The real world isn't that clean. So how does this super logical way of thinking handle all the gray areas, all the uncertainty we have to deal with every single day?
Exactly. I mean, a patient might have a slight fever, right? A statement could be mostly true. How do you represent that? Standard logic programming, in its purest form, really kind of struggles with this. But of course, the field has evolved.
So to handle this, logic programming brings in ideas like fuzzy logic.
Instead of a statement being 100% true or 0% true, it can have a degree of truth or a degree of membership. So a statement like, the patient has a high fever, could be, say, 85% true. And this lets the system reason with uncertainty, with things that aren't so black and white.
And this ability to adapt doesn't stop there. These same ideas help manage really complex open systems where you have multiple AIs that might have conflicting information. But maybe the biggest advantage of all is verification. Because everything is built on formal math, you can actually prove that a program is correct. This means you can be certain that a critical system, like an aviation or medicine, will behave exactly as it was designed. That's a level of assurance that is almost impossible to get in the probabilistic world of machine learning.
And that leaves us with a final thought. In an age where a lot of our AI models are black boxes, they're incredibly complex and sometimes unpredictable, there's a real elegance to this rule-based approach. So the question is, as our AI systems get more powerful and woven into our lives, will the provable certainty and the transparent reasoning of logic programming become not just an alternative, but an absolute necessity? Something to think about. Thanks for watching.